In my this last lecture, I'd like to first continue the topics of this boundary conformal theory to holographic dual, and especially I'd like to explain the holographic dual of boundary entropy and the holographic dual of entanglement entropy. And the final part of my lecture, in this session, I'm going to talk about our recent work of the calculation of entanglement entropy in moving mirror setup, which also beautifully reproduce Page curve, which is also related to black hole information problem. Okay, so let me start with this boundary entropy. Last time, just end of my last lecture, I talked about these slides, and I introduced this boundary states, and now I'd like to introduce the boundary entropy. And boundary entropy is actually defined. There are three different definitions actually. So these three are actually equivalent. These three is equivalent, but first one is the simplest one, which is just say boundary entropy is just log of disk amplitude, right? This amplitude actually described by inner product of vacuum state and the boundary state, right? Because boundary state is making hole, and the vacuum state is just part of the sphere. And so, and the point is that we just take a log, and this is the entropy. And the reason why this is entropy, I will explain later. Just so you can understand this entropy nature from this definition 3. So, but let me next talk about definition 2. This is actually using cylinder amplitude. This is actually quite equivalent to definition 1, but it's more convenient to fix overall normalization because this amplitude has a UV divergence. Right, we have to regulate it, and it depends on really highly depend on normalization. But cylinder amplitude is quite normalized. Cylinder amplitude means we have two boundary alpha and beta, and some open string connect between them, right? And the open string is a one loop diagram, right? Or you can see this closed string is propagating from alpha, D brane alpha, and D brane beta. But I'm not talking about string theory, just conformal field theory, boundary conformal field theory. In that case, we have a cylinder amplitude, right? It's an overlap between two boundary states, which create alpha and beta hole, and with some length L, right? Large L. And its length is exponential HL, right? This is a time translation, right? We regard this as Euclidean time direction, exponential HL, and assuming that L goes to infinity, right? So we take this length is very, 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 very large. Very, very large. So that in the limit, so only ground state, from the viewpoint of closed string, only ground state propagates. So we have just ground state energy of this, string, closed string. And then, and it's a closed string propagation with some disk amplitude. So we can regard this as a kind of, diagram like disk amplitude, to disk amplitude, and with just ground state propagation. And this part is just this part. And this first disk amplitude is this guy, and second disk amplitude is second guy, right? And okay, and that way we can understand the relation between disk amplitude and cylinder amplitude, right? So it's like square of disk amplitude appears, right, in the cylinder amplitude. And anyway, by using this, you can extract each of G alpha and G beta, and this is another definition of boundary entropy. Taking log of this guy, you get the boundary entropy. And finally, you can define entanglement entropy, right? So we can talk about some space with boundary, some boundary, right? Like this boundary. And that case, you can regard this as Euclidean time direction, and this is a time slice, right? This is we take some time slice tau equals 0, and decompose Hilbert space into A and B, right, as usual. But here we have a boundary. Always we have it's like semi-infinitely extended space, right? And in that case, if you calculate entanglement entropy for this region A, you can naively think this is a kind of doubling trick. You can think about some mirror. You have a mirror across this mirror. You have a mirror charge across the mirror. So there is some twist operator here, and there are some mirror twist operator here, and they're like 2-point function. And then you get again this length is L to L, so it's like 3 over C log L over epsilon, right? But it's because this is a mirror, so we cut it into half, right? Only half contribution, like C over 6. Right? You just half of the result. Roughly, you can understand this part. And second part actually comes from the nature of boundary. And indeed, because if you calculate this entanglement entropy, so using replica trick, it then involves disk amplitude. And that's the reason we have log, again, we have disk amplitude, namely log G alpha. So that way, but this is exactly boundary entropy. So that way, the finite part of entanglement entropy is actually coincide with a boundary entropy. And indeed, that's the reason why we can think boundary entropy as entropy, right? So at least some part of entropy. Okay, so these are three actually equivalent, all related to this temperature because of the reason I just mentioned. And if we look into the holographic dual, how we can calculate, right? But we know, right, how to construct gravity dual of disk, for example, disk. Or we just talk about, upper half plane, like this half plane, semi-infinitely long, semi-infinite plane. It's holographic dual. We have some boundary surface Q, right? And it's like this region is a gravity dual. But you can actually conformal map, right? We can do some conformal map. From here to here, around the sphere. So that way, actually, conformal mapping is well known, right? This is well known conformal mapping. This special conformal transformation, basically, and the mapping from this maps line to circle, right? This is quite well studied. I mean, well known textbook, like But then we can have a bulk extension, right? And Z also changes. This is obtained by, for example, this earlier paper. And we know how to do this in area safety, so we can have a gravity dual. And this Q surface now mapped to a part of sphere. So it's like a sphere. Like this sphere is given by this equation, right? Tau is a Euclidean time, right? X is this X direction, and Z is this direction, right? And it's like sphere. And this center is this value. It depends on rho star. Rho star also related to, rho star is this angle, right? We discussed a little bit, right? Before, right? Rho is this Q is fixed by rho is rho star, and rho is minus infinity here, and rho is plus infinity here. Right? Rho is this kind of coordinate, so hyperbolic orientation. And the rho star is related to also tension of the plane. Tension of the plane. And depending on the value of tension, this location changes. If tension is very large, it's actually center is like this is a very huge, you get a very huge boundary, but if tension is very small, then, if tension is very, very small, so it's like this, then you have like this. And even you can go negative tension, it's like center is outside, so that means, boundary surface Q is very, very narrow, very small. And that way, anyway, we can find holographic dual. And once we know the gravity dual, we can evaluate gravity action, okay, gravity action, and we can prove this configuration, and then we have divergence, UV divergence, and so on, like this. And so here we talked about the ADS3 example, right? ADS3 example, and dual to BCFT2. So lowest dimensional, basically lowest dimensional example, and then the quadratic divergence. Epsilon is, of course, UV cutoff. Here you have epsilon, right? This direction, and Z equal epsilon is UV cutoff. And then you have divergence, and the linear term actually depends on the rho star. And importantly, so we have logarithmic divergence. This is just come from conformal anomaly. This is conformal anomaly contribution, and some finite, constant contribution. Okay, some constant contribution. Like this. Okay. And this constant contribution is very important because we can remove divergence by renormalization, and you can remove this divergence. Then what we get is the most important part, which is but very universal, cutoff independent quantity, which is actually given by rho star. Rho star divided by 4G Newton. And you can rewrite this in terms of tension, right? That's using previous formula, which I gave you. You can rewrite this T is a tension. Right? If tension gets larger, this arctangent hyperbolic, so rho star also gets larger. Okay. So this is our expression, a precise relation between tension, interpretation of tension. Actually, in ADS-BCFT, tension is interpreted as boundary entropy by using this formula. And then we can go a little bit more. And okay, so this is there is actually okay, so we can actually calculate the boundary entropy and for annual partition function. So I talked about three different definitions. Okay, so we talked about three. So here let me go back. So I just holographically we computed already, right? Boundary entropy from this approach disk amplitude. Now I go to cylinder amplitude. Right, we want to have some holographic dual of cylinder. So that is actually obtained in the following way. So at finite, so it's depend on temperature. So we can change temperature. High temperature we get a black hole, as you know, the Hawking phase transition. And so at finite temperature there are two solutions actually. So thermal ADS and the low temperature phase solution and the high temperature phase, which is black hole. Right? This is a non-black hole. This is a black hole. And always we are interested in, because we are talking about annulus amplitude, right? So annular amplitude is like this, annulus is like this, right? So we have a strip here, right? It's like strip. So there are actually, in the morning there are questions about strip. So we are talking about this in the strip. This is x direction and pi z 0, right? So we are interested in the gravity dual of this setup, and its one boundary is alpha. Sorry, we have two boundary anyway. So we want to calculate, gravity dual of this conformal field theory on a cylinder. And let's go. This is length is just called pi z 0, and then there are two solutions. And the Euclidean time direction is this Euclidean time is identified with this way. Okay, this is a spatial next, and ZH is related to temperature, effective temperature, because it's an inverse temperature is the periodicity of Euclidean time direction. And then there's so low temperature phase. It's much like in thermal ADS is given by this thermal ADS solution, and high temperature phase is this black hole solution, right? Because tau shrinks to 0 size, but this is spatial direction, circular direction shrinks to 0 size in ADS, global ADS or ADS soliton or thermal ADS. So we can, but this is just a bulk solution, so we have to cut out the geometry, right? So we cut out geometry like this, and we need to solve boundary Einstein equation, right? Which is given by especially KAB equal to HAB, some constant and depend on the this is a tension. This is not temperature. This is a tension. Depend on tension. It gives this boundary Einstein equation. Basically gives two differential equation. One differential equation. This is for lower temperature, and this is a high temperature. Right? We can, but fortunately we can solve this differential equation and analytically for ADS3 example. So this is here are solutions. Right? Low temperature solution looks like this, and high temperature solution looks like this. And then how do they look at? That's what I would like to explain. Okay, so here are the explanation. So this is a low temperature, right? This is a low temperature solution. So you have like soliton-like geometry originally. This is ADS soliton. And so I'm not writing, tau direction is outside. Tau direction is just a circle, S1, right? Tau coordinate is just S1. And tau is always circle. There are no topologically non-trivial thing happens for Euclidean time because this is like ADS soliton. This is a sort of global ADS, global ADS3. So, but the point is that this spheric spatial direction, this is a x direction. X direction is shrinks to 0 size at the tip. And then, so the gravity dual, so we are talking about gravity dual, and this is the interval which we are looking at. Right? We are talking about the gravity dual of this guy is actually turns out to be this region, right? This region. This is a boundary surface. This is a boundary surface. Boundary surface, I can write it to green. Sorry. And this is a boundary surface Q, right? This is a boundary surface, and this is a M is a boundary interval, right? And so gravity dual is given by this. This is a low temperature phase. And on the other hand, if we go to high temperature phase, there time again we have a tau direction, right? We have a tau direction, but this can be actually tau direction shrink to 0 size, at the horizon, exactly this point position. This is Z direction, right? And but if we look at the X direction and Z direction, it's like this. And so boundary again, this M is here, right? M is situated here, and the boundary surface Q actually they disconnected into two parts, right? Disconnected. This is disconnected. This case is connected. Disconnected. This is a phase sort of phase transition, and there is actually one more interesting ingredient, namely horizon. You have a horizon, right? You have a black hole horizon here. So Q end on the horizon. So this is what's happening in hyperbolic phase. Right? This is, and the gravity dual is this region. Right? N is a gravity dual of BCFT. Okay. And then, so we can, once we know the geometry, right? And but of course, this curve, right? This curve is specified by previous these formulas. I'm not going to details, but you can confirm that. And then once we know the geometry, we can evaluate partition function. We can just evaluate on-shell gravity action. Okay. Then low temperature is very simple, like this. This is temperature. Huh? It's like a proportion to beta, inverse temperature. Huh? Because low temperature, always low temperature phase is proportional to action proportional to beta, right? Because beta is time, periodicity in time direction. It's just simple integral, just beta. But the high temperature phase is non-trivial. Right? High temperature phase, you have a non-trivial because you can remember that, and it's integral truncated at the horizon. And also, there is a contribution from this Q surface, right? And this Q surface contribution actually gives boundary entropy contribution. This you can confirm this in an explicit calculation. There are no, even though there is a boundary here, actually this does not contribute in a low temperature computation, low temperature phase. And in only in high temperature phase you can confirm this actually. We have some boundary entropy contribution. And this part is just standard thermal entropy. This is standard. This part is just standard thermal entropy. This part is thermal. Okay, there is actually a question. So let me. Oh, is induced metric on the Q brane a lower dimensional black hole metric? Yeah. Okay. So Q is that's right. Yeah, this is ADS2. Yeah, ADS2 metric with black hole horizon. Yeah, that's right. ADS2 black hole. Because it's like just we have cut it into this way. Yeah. Okay. Yeah. Then. Okay. So anyway, so we have some two evaluation, like low temperature phase and high temperature phase. And then we can talk about actually details of the phase transition, actually, phase transition. So this is here I plot this, I plotted the preferred phase. This is BTZ phase, this is black hole phase, this is thermal radius phase. And this horizontal axis is tension. This is tension. This RT is T is tension, basically. This tension. And this vertical axis is temperature. TBCFT is a bit confusing, but temperature. So high temperature, basically high temperature phase, right? If you go high temperature, you get a black hole phase. At low temperature, you get a thermal radius. But the results, phase transition temperature depends on the value of tension, right? If we go to very large tension, it's very a lot of degree of freedom as a boundary. So very easy to go to black hole phase. This is a maximal value. We cannot go beyond. This is a maximal value of tension. So you can, if we go here, it suddenly very quickly goes to black hole phase because already boundary provide a lot of degree of freedom. But if boundary entropy is very, very, so this boundary entropy here is boundary entropy is actually gets divergent here, right? And here, and this is also another boundary, and T less than 1, this RT equal 1, this RT equal -1. At this point, G function actually goes to 0, so boundary entropy goes to -infinity. Boundary entropy can be, can be negative because it just say we just talk about finite part of entanglement entropy. Entanglement entropy should be positive because it includes divergent piece. But if we remove divergent piece, this boundary entropy can be negative. So here it's maximally negative, this is maximally positive. And if boundary entropy is very small, quite a long time, thermal radius is preferred, right? Because the degree of freedom is very small. And after that, at quite a high temperature, BTG phase appears. So you can confirm. And indeed, this phase transition temperature, you can get this kind of analytical formula for this. Okay. But anyway, yeah. So these are right. Gravity dual of the annulus. Okay. Okay. So then I would like to go to this boundary entropy, final definition of boundary entropy by using holographic entanglement entropy. Here, the prescription by using, like island, like, configuration of holographic entanglement entropy plays a crucial role. This is a quite nice test of the prescription. So so this again, we go back to original setup. This is half plane, this is a boundary. This is CFT lives on this manifold is a boundary here. And this boundary is extended in the bulk, right? This is surface Q. And the physical region, gravity dual is this part. And then we talk about subsystem A, and this is a Euclidean time. This is the same setup which we previously saw. And this is a subsystem A, then this is the end point. So we can talk about the minimal surface, which end on Q, right? You don't need to necessarily end on Q, but then it's like what this is. But this Q, this guy, it has a smaller length, actually shorter length. And so this is just the integral of rho direction, right? Just the integral of rho up to rho star. So then you can calculate it. This is something familiar term, which I already explained for BCFT. But we have this boundary, right? So this is a boundary. This part is boundary, finite piece. And this is exactly here. So this value is precisely rho star over 4G Newton is also already we saw, right? We just saw before. Yeah, here. Right, this is same, right? You can get the same value as this amplitude and also, oh, sorry. Okay. Yeah, and also annulus amplitude, and also finally, like this is entanglement. So in this way, we can derive boundary entropy by using ADS-CFT correspondence. Okay, and so next question is G theorem, right? So this boundary entropy has a very nice property that monotonically decreasing under RG flow. So can we see this in ADS-CFT? So the answer is yes. And so we can, for this, we can assume this metric, just Poincare metric, and putting some boundary surface Q, right? And we need some assumption always. For example, if we want to derive C theorem, we need some energy condition, and always this energy condition we use is something called narrow energy condition. Narrow energy condition. A narrow energy condition is like, if we contract this energy stress tensor by any narrow vector, it should be positive, right? So we are assuming narrow energy condition for boundary matter, not the bulk matter. Boundary matter which localize on the surface Q, right? And then what we need to impose this, then we can write this equation, but because we know, right, TABQ is equal to TKB and KHAB, right? This is boundary version of Einstein equation, which I explained, right? So going to this relation, so you can just evaluate this guy. This should be also positive, right? And this is just the geometrical quantity and given by this roughly second derivative of x. X is profile, right? So we have like we have x direction and z direction, and I'm talking about surface Q, right? Surface Q is something like this, and this is this is profile given by x equal xz, right? Something like this, for example. If you have in mind, some surface Q is like this, and this second derivative appears. Okay, and then we'd like to impose this should be positive, right? And so we need we impose this null energy condition, right? So that means this guy is always positive, and this means x prime prime is negative, right? Because it's a minus sign. And but let me remember what is happening here, right? Actually, this gives a G theorem, as we will see. But anyway, so this is x. I just write it x direction and z direction, right? And we want to define somehow holographic G function by this ratio, basically xy over z. So we have in mind some, so let's take this as some manifold M. We want to construct this gravity dual of this guy. It's actually go this way. It's actually go this way. This is surface Q, right? Surface Q, maybe I just write it purple. Surface Q. Surface Q is like this, and this is of course x equal xz. And basically this angle, tension, as we saw this angle here, right? Angle here is basically tension. And this tension is directly related to G function. At a fixed point, this is true. So it is quite natural to take this ratio, x over z, right? X over z. And this is a fixed point, this is rho star, as we used, right? But actually, we can show if we take derivative of this guy arc hinge and this ratio, right? And this is the reason we take arc hinge, we just want to extract rho star at a fixed point. This is just rho star. This guy is just rho star. And we know, right? Rho star divided by 4G Newton is a boundary entropy at a fixed point. So that's the reason we have this formula. But we just generalize this formula for any rho star, for any z, any shape of Q, so that we just take this ratio. And then, so we take a derivative anyway. So then we have this, but this is actually turns out to be negative because of this relation. This second derivative appears. Anyway, we can, assuming this null energy condition, this derivative is negative. So that means angle is actually decreasing, right? Angle is decreasing. So here we have a, bit non-trivial, gradient, but its gradient should be gradient should decrease, goes to 0, like this. So it's like we should have this boundary, but not like this. This kind of boundary is not allowed, right? This angle gradient should decrease. And at d equal to that fixed point log gz is agree with boundary entropy, right? As we say. But in higher dimension also, anyway, this kind of theorem is true. So we expect this is kind of higher dimensional generalization of G theorem. Okay, so these are holographic kind of argument. Okay, and then, but let me summarize this holographic G theorem, which I explained here. So by imposing null energy condition, this TQ, this contraction should be positive. And then we can prove this holographic G theorem, namely, so G function is defined by arc hinge x by z. This is basically, you can take this g, xz, and just take a, this angle. Basically, this is this angle, right? And this angle should decrease. Angle is originally this angle, but it's like going to, gradient should be, go to 0. A gradient, right, from x direction. So this is some non-trivial angle, but its angle is this angle should be decreasing under RG flow. But this is also interesting from geometrical viewpoint. Actually, because of this, and we cannot have this kind of configuration. So this actually prohibits some kind of wormhole, like traversal wormhole. So you can imagine two boundary A and B, and we want to construct gravity dual of this disjoint union of A union B. But that case, you might think there are actually this kind of wormhole configuration. But here we assume actually, so there are some assumptions. We assume static space-time, static background, and one might think there are some this kind of wormhole, but this is not possible because you see, right? This kind of profile of boundary surface is go this way, opposite way, right? It should always go this way. We cannot connect, two different disjoint in turn. So we should be very careful. This is kind of boundary generalization of this topological censorship, which is well studied by GR people. Okay.
Tadashi?
Yes.
So at the quantum level, should we expect to use the quantum null energy condition or average null energy condition? Or?
Quantum level. Okay.
Because
yeah, I think so. Yeah. In quantum level, if null energy, if null energy condition is correct, then I think we can also derive this kind of result. But as you know, like null energy condition is violated because of quantum effect.
Right.
And I'm not sure about the quantum null energy condition. So we have QNEC, but I don't know what QNEC predict in this case, actually. Yeah, that's interesting. But of course, if we allow some non-trivial, I mean, like some interaction between A and B, like causal contact between A and B, like double trace deformation, then we can create. We should be able to create traversable wormhole, as we know for the case without boundary.
I see. Thank you.
Yeah, and also I don't know about I don't know what average null energy condition tells us about this kind of setup. But I think that's quite interesting, especially about the quantum energy, null energy condition.
Okay, thank you.
And yeah, but nevertheless, even at this classical level, we can actually construct some wormhole. This is the next part. This is actually time dependent. So if we allow time dependence, then we can construct traversal wormhole. This is not traversal wormhole, but some wormhole. So this is actually a very simple example. So actually related to previous example, disk or gravity dual of disk. Right? It's like just part of sphere, right? So we can write down sphere in ADS space. We cut and pick up this region. This is a gravity dual, right? This is a ADS sits at the ADS boundary, and this is a bulk extension, right? The bulk extension of the stuff. But we can do some analytical continuation. Just we do tau goes to I tau. Then we get this geometry, right? This, if we put plus, this is a sphere, but it's just minus. It's like hyperbolic, right? And then we have this geometry, and this geometry we can write this way, right? This is a gravity dual. And as a boundary, you can set epsilon, you can set z is 0. Then this is a geometry, like A and B actually is extended this way, right? A and B are extended. So I'm talking about outside of this part. So it's A and B is situated here. And they are actually entangled with each other, but there are no causal contact, no interaction between A and B. There are no, they are causally disconnected because you can send signal from some part of B, and it's always outside of right cone of A, right? You can send A, but it's outside. So that way, there are no interaction, no causal connection, but there are some entanglement, quantum entanglement. And because of quantum entanglement, the geometry actually connected like this way. So this boundary is exactly this boundary, but they are connected in the bulk. They are connected in the bulk like this. We just this geometry is precisely just described by this equation. It's obvious in some sense. So that way, anyway, if you want some wormhole, you can create like this. And if you have some non-trivial causal interaction like double trace deformation, then slightly you can shift, probably you can shift profile of boundary, then you will get some traversable wormhole. You can send signal. Yeah, and in the BCFT side, so there are these two BCFTs are entangled with each other, as I explained, and the entanglement entropy between this region and this region, actually it's just length, right? This is a wormhole and cross-section wormhole, namely this length, geodesic length. This is exactly this one. This length is precisely this one, gives entanglement entropy. Right? And but this entanglement entropy, you can regard this as a kind of part of black hole horizon, black hole entropy, part of black hole entropy. So because this is a setup which we talked about, right? So this setup we talked about is depicted here, written here. But you can do some coordinate transformation. This is a familiar coordinate transformation from Poincare ADS to BTZ black hole. This is a BTZ black hole. Then this red guy goes to here, and the green guy is across the horizon, right? Across the horizon, and this is a cross section. So I should write it this purple line. This is precisely mapped to horizon, and this green guy is outside. And this is just a simple coordinate transformation. And so this entanglement entropy between A and B, namely this cross section, then precisely coincides with black hole entropy, part of black hole entropy. So this is what's happening here. It's much like just generalization of sum of U double prescription of ADS black hole. Okay. Okay, so now I would like to go to, so these are basically, here I just finished a basic explanation on how gravity dual works in ADS BCFT, the gravity dual of, theory with boundary. So now I'm slightly go toward more black hole information paradox. And so to connect this kind of argument to the case with gravity, of course, black hole information paradox is very, the reason why black hole is very interesting is because it's interacting through the gravity. Gravitational interaction is very, very important. So, but normal ADS safety relates conformal field theory to ADS gravity. But in the CFT side, there are no gravity at all. Like gravity is decoupled. But anyway, if we want to include gravity in CFT side, then we have to do something called brainwashed holography. This is the thing which I just quickly review here. So we have like, ADS space-time, right? This is familiar Poincare ADS space-time, but normally we put boundary at z equal and z equal a or epsilon, and epsilon goes to 0, right? And this is because epsilon is cutoff scale. But what about if we take a to be finite value, like ADS radial scale, then there are no decoupling between gravity and gauge theory. And moreover, we impose, we impose this on the boundary, we impose Dirichlet boundary condition, but we change boundary condition. Let's impose Neumann boundary condition. Yeah, Neumann boundary condition. Then what happens? Right? If we impose Neumann boundary condition, as we discussed in ADS BCFT, there are some dynamical degree of freedom, right? Some gravitational wave degree of freedom localized on the boundary, right? Some existing on the boundary, because metric can fluctuate. In this setup, actually, d-dimensional gravity is localized. You can also call this is a famous result by Landau-Sandram. And if we talk about gravitation in d+1 dimension, but it's some degree of freedom is actually localized. Gravitational degree of freedom localized on this plane, d-dimension. So we have some d-dimensional gravity theory in this setup. And yeah, so that in the end, the claim is like this. This is a brainwashed holography. But this is kind of a little bit ambiguous. We don't have a precise understanding of this. That's a kind of little bit weak point. But this is quite, once you admit that, it's very, very powerful. And yeah, the claim is like this. So classical gravity on ADS d+1 with Neumann boundary, right? This is exactly this one, right? So this is ADS. We have ADS d+1 here, right? And with some boundary, and we impose Neumann boundary condition. And A can be, any value, so not necessarily small. And then actually, so we talk about this, then actually this is equivalent to, so this is a kind of sense of ADS CFT, right? This is the ADS side and there are CFT side. And then CFT side actually is actually quantum gravity. Right? So of course we have a CFT in the sense of ADS CFT, but it's also metric is fluctuating because we are imposing Neumann boundary condition. And this fluctuating metric means, of course, gravity, some quantum gravity. We don't know precisely what this quantum gravity is, except some explicit examples, but it's kind of quantum gravity. And then, so we can also estimate the Newton constant of this quantum gravity, lower dimensional quantum gravity, like this way. So that we start from, like Poincare metric, and this is we can start with d+1 dimensional Einstein-Hilbert action. And we plug this, this part is fluctuating. This ansatz, right? This is a d-dimensional metric, and we plug this here. And then we can extract, curvature, a rich scalar for this h mu, lower dimensional gravitational theory. And then we can regard this guy as a lower dimensional Newton constant, okay? This is a lower dimensional Newton constant. That way we can relate this higher dimensional Newton constant to lower dimensional Newton constant with some factor. Right, this A is a cutoff scale, right? A is just as we introduce this is Z direction, and we introduce, like this, Z equal A, right? And this is the effective Newton constant for this theory. And we can see actually the implication of this relation. So we can to see that one way to see that let us reconsider holographic entanglement entropy. So you can just think about the holographic entanglement. So we have like some surface A, right? And so we have some gamma A here, right? We just calculate area. And in that case, we can calculate area, but if we literally do that, please remember the thing I explained yesterday about to derive area law from holographic entanglement. This is area law piece. A is this cutoff, so this area law divergence, right? And plus some correction. That's fine. There are some corrections. 1 over epsilon corrections. Epsilon corrections. A corrections. And this is the overall factor. But if we focus on this area law piece, this is actually you can regard because this A appears here, right? So this is exactly this relation, right? This relation. You can just use this relation to absorb this factor. Then you get a lower dimensional Newton constant, right? And the area of boundary. So this is much like lower dimensional gravity. Yeah. So this is a kind of looks like a gravitational entropy in lower dimensional gravity. Right? The Bekenstein-Hawking horizon. A can be, boundary of A can be horizon, but not necessary. But anyway, or we get some gravitational entropy. So that way, indeed, we can have some lower dimensional gravity and which are the correct gravitational entropy. This is a kind. This is and the higher order looks like like quantum corrections because we have like some sort of quantum gravity here. So this is a kind of interpretation, and so we can see like, roughly how this kind of proposed brain-wide holographic relation makes sense if we think about the entanglement.
Sorry, Tadashi.
Yes. Yes, sure.
So this the coupled with CFD dimension is that CFD is the dual of the original bulk, or which CFD is that?
Yeah. Original. So this CFD is same CFD which arises ADS CFD.
But then, since the brain gravity is also reduced from this bulk, is this something overcounting?
Sorry, what do you mean? No. This is if we talk about the ADS 5 crosses 5, right? And cut in the middle, this is just n equal 4 meters. And this gravity is just fluctuating metric in n equal 4 meters. But we have some cutoff scale, of course. This is we have a CFT, but we have a cutoff scale of this energy scale A. So that reduces degree of freedom. So does this answer your question?
I see. I just wondering is this this reduction gives this d-dimensional gravity is also from the reduction of the wedge, but the original safety T also due to this ADS.
Safety D, yeah, already. But if you
looks like something overcounting.
No, CFT is dual to ADS gravity, right? And then if you couple CFT to gravity, actually that reduces degree of freedom. Because it's also introduced in cutoff scale.
I see.
So because this CFT is only defined up to some scale, up to some scale which is related to A. So it's a quite a UV cutoff. Finite cutoff CFT. So I don't think this there are some overcounting of degree of freedom here.
I see. Thank you.
Okay. Yeah, and so okay, and we can also generalize this to the case where this A is a real black hole on the brain, right? On the brain, right? You have a black hole here, higher dimensional black hole, but lower dimensional black hole. This is done by these people, and in that case, you can understand, black hole entropy in d-dimensional gravity, by using brain-wide black hole, right? So that case, brain-wide black hole quantum black hole entropy is related to classical entropy in the one higher dimensional untitled space. Okay, and right. So yeah, here let me go further, and there are some kind of interesting duality chain, three kind of tri-duality, right? There are 3 different pictures. So one is this one. This is just boundary CFT, right? So CFT, which lives on the manifold with boundary, and we already see by using ADSB CFT, we have a manifold M, and this boundary is extended in the bulk of the surface Q, right? And there are some wedge of ADS space. And finally, so as we just reviewed here, right? There is a brain-wide holography. Right? Brain-wide holography tells us that starting from this setup, this is exactly brain-wide setup. More precisely, this is Cauchy-Randall setup rather than Randall-Sandler setup. But it's anyway, this setup, in this setup, so you have a Neumann boundary condition brane, right? So this here we have a Neumann boundary condition imposed on Q, right? And this guy actually has a dynamical degree, dynamical gravity. And actually this is really brane world. So that says we have some gravity coupled to this CFT, right? You can regard this way. This way. Of course, there are some CFT degree of freedom, cutoff CFT degree of freedom, see hidden here. But anyway, gravity coupled to CFT along this border. So these three descriptions actually equivalent. So this is very important to understand further physics related to black hole. But also there are another application. I don't have enough time, but I think you can refer to Jishat's Gong Show talk tomorrow. This is about the codimension 2 holography. Also this Yan Zhou wrote a very interesting paper also this codimension 2 holography. But there are, I think, also many other applications of this duality chain, right? It's like boundary, conformal field theory, and the ADS BCFT, and brane world. Right? And so, and I'd like to explain the application to black hole information paradox. And already we had a talk by Henry. I think so you understand the motivation and so on. And yeah, but then as a crucial formula, which involves this black hole information paradox in the recent development is island formula. So I also explained, a little bit explained in the last lecture. So island formula basically says us, we have some CFT coupled to gravity, right? And both are D dimension. And we define subsystem A in CFT. We don't want to introduce subsystem in gravity. Maybe it's possible if gravity will, but let's try to avoid it to make everything clear, right? So we just introduce subsystem A in CFT. Then we can calculate entanglement entropy. This is quite well defined, right? Just Hilbert space factorize and A. How we can compute entanglement entropy A. Right? Without gravity, we know, right? We know how to do this by using holography or replicatory. But if we have a gravity, non-trivial thing happens. And the answer is simply summarized in this island formula, right? And they are worked out many people. And so there are two terms competes, right? One is just entropy. So one term is the standard one, just entanglement entropy, because we are talking about entanglement entropy. But not only A, but also we include some region called island in gravity, right? If island is trivial, right, this is just standard entanglement entropy. But let's add some island contribution. And we also need to add some area contribution of this gravitational entropy, because this is a gravity, right? Once you cut space into two parts, always there are some edge moduli contribution, which is just area divided by 40. And there are two contributions. We have to sum of both of them and take minimization, right? Sometimes there are no island. This island does not minimize area, but sometimes existence of island is important. And but actually, we can understand this situation by using this BCFT. Right here, also we combine this brane world gravity, which I explained here. Right, so we use this three-part duality. Right, we use this one. So we can go from here to here. Right. So anyway, by using this brane world holography, right, we have some CFT here, right, just map to here, and this gravity, we can regard this gravity as a brane world gravity, right, brane world holography. Then it's like this surface Q appears. But once you have this setup, this much like ADS BCFT, right, ADS BCFT, and Q is the end of the world brane, Neumann boundary, and then we can calculate entanglement entropy A by using holography, and then using this ADS BCFT prescription, and just this minimal surface end on the boundary of Q, right? And we have to minimize as I explained. And this is precisely coincide with this formula, right? So this way we can understand this island formula very naturally from just more standard ADS-CFT involves ADS-BCFT. And this actually explains, as worked out many wonderful papers, so we can derive so in many different setups, we can derive page curves by using this technique. And I will give some simplest example first, and then go to a final issue of this moving mirror. Okay. And already, I think page curve is already explained by Henry, so I don't need to explain this, but just quickly remind you. So we are talking about black hole evaporation, right? So initial black hole and Hawking radiation, in the end, no black hole at all, and everything is radiation. So we decompose Hilbert space into two parts: black hole Hilbert space inside the black hole, and just radiation part, right? And as you know, like SA equal SB relation, we assume pure state and it's a unitary evolution. This is, of course, always starting point of black hole evolution. So we assume black hole is pure state and unitary evolving. So then entanglement entropy is initially increasing because, initially black hole evaporates and there are small entanglements start, radiation and black hole start to entangle. And at the middle time where black hole is, half of black hole evaporated, then radiation and the black hole is a maximally entangled, highly entangled, right? Maximum amount. But after that, right, and black hole shrinks. So radiation, there are a lot of radiation, but this radiation cannot be entangled with large part of black hole because black hole itself is very, very small, right? In the end, should go to zero, right? So this is a page curve. It's like increasing, but at the middle point, it's going down. But if we naively think this, radiation is just kind of mixed state radiation, thermal radiation, its entropy is always going up, right? Thermal entropy is always going up. So we have this kind of very huge gap between this. This is a, basic problem of this black hole information paradox in the language of page curve. But there are some clever derivation of this page curve, especially by using, like holographic approach involving brain world and ADS-BCFT. This is first found by this Al-Muheri, Mahajan, Marza Sena, and Zhao 2 years ago. So here I give some sketch of this derivation. Okay, and so this is a kind of we are modeling in the black hole evaporation process. And so we have some boundary here. This is a familiar set of ADS-BCFT, or looks like the ADS-BCFT. Here is a CFT, this is a CFT, boundary CFT, and this is kind of surface Q. You can regard the surface Q. And this surface Q, you have a ADS gravity, right? Gravity coupled to CFT here. But there are some also, you can put some black hole here, right? Some black hole horizon. But at t equals 0, there are no, let's assume, right? We want to describe radiation, but at t less than 0, there are no radiation. That means these two guys are separated. Let's assume these two guys are completely disconnected. So that case, we can realize holographically just cutting geometry into two parts, right? This geometry and this geometry is independent. There are no interaction at all, right? And this gravity sector and CFT is completely decoupled. And if we talk about the entanglement entropy of this region is supposed to be radiation because the black hole is here, and in the end, black hole here, and the radiation comes to this left part, right? So this radiation Hilbert space, and we call it as A, right? And then we calculate holographic entanglement entropy. Let's put some small, small slit here. So then entanglement entropy just this area, right? Gamma A, right? Gamma A, very, very small. This is very, very small. But once you join, right? This is kind of described by kind of so-called joining quench. Joining quench. This is kind of one of quantum quench. So once you connect this, it's like they connect at this point, right? We suddenly connect, then we connect it. So UV part is connected, right? Suddenly, interaction. Then actually this kind of we have a slit here, right? Slit is going down, right? So initially it's cut it out, but it's like a slit squeeze this way, and finally going down. This is typical in a joining quench. And that case, you can think there is a boundary. This is a BCFT boundary, right? So as we discussed, this minimal surface can end on the boundary surface, right here. Also, these are also boundary surface because we impose Neumann boundary condition. But anyway, before that, this is initially at least this guy is closer. This is a entanglement entropy. This length is entanglement entropy. So it's increasing, right? Because this guy is going down. But at some point, right? So this guy, importantly, because of this prescription which I explained, ADS-BCFT, this can end on also another Neumann boundary, right? This surface Q. So then you go this way. This is much larger. Right? If the slit going down, then this gamma prime A is much larger. Right? Length is much larger, much longer than gamma A. So this guy favored. So at this point, there are some phase transition, right? Suddenly going down, and because of this, a black hole evaporating, and this actually in the end going down and disappear. So this is a very, kind of toy model, but it's kind of heuristic sketch how page curve is understood, from ADS-CFT correspondence by especially using the brain world and ADS-BCFT like description. So this is a kind of, and of course there are complementary, approach using so-called replica wormhole, which I think Henry will talk about. So, but for my talk, I'm just wanted to finish at this point, and I go to final topic. But let me summarize here. So we have this island formula, and by just coming from energies from ADS-BCFT, so as already mentioned, so we compute entanglement entropy for region A, and to calculate entanglement entropy with the boundary, Neumann boundary, we can end this end of the world brain. We can end, minimal surface can end on the boundary of A, boundary of Q, and you can choose any shape of B, right? So you have to minimize also B, right? So this is a minimization. Sorry, yeah. So B is just same as island, right? So we have to minimize, and also of course we have to minimize gamma A, but yeah. So we have to minimize both this shape and also this ending geometry, and we have to sum over both contribution. But this actually just both are originally just single area. Okay. Okay, so I'm now going to my final topic of this moving mirror calculation. But if you have any question, maybe it is good to ask now. Okay, but there are some questions actually. So, sorry, in the chat, this brain world holography, the brain seems to be at constant Z, but for BCFT case, end of the brain switches at non. That's right. Yeah. For BCFT, so we use actually for BCFT it's like this, right? But it looks like nice coordinate. There are nice coordinate low star, right? As we introduced. Let's call this is the ADSD, right? So ds square and ADSD plus 1 metric is written in terms of this hyperbolic or ADS patch, right? As we explained like this way, right? This is a low coordinate. And then low is low star, fixed is, a kind of cutoff, z equals this, analog of z equals this star. So a little bit different. So this is called Cauchy-Randolph setup, but this is the original one. This is Cauchy-Randolph. This is the original one. It's called Randolph-Sandler setup. But they have some similar property, like localization of gravity and so on. Let's see. Another question, can BTZ metric be written like this using low coordinate? Low coordinate. Sorry, maybe, yeah, I don't get the precise point of this question. Maybe yeah, maybe more explanation. Sorry. Can be added, no? So of course we can talk about the BTZ metric, and but the BTZ metric, yeah, of course, a BTZ metric is locally ADS3, so you can always rewrite BTZ metric in terms of Poincare ADS3, and then you can map to low coordinate. That's true, but it's a bit complicated. This low coordinate is complicated in BTZ metric. Using rho and y coordinate. Yeah, I think answer is yes, but it's a bit complicated. Because anyway, you can always map to BTZ, right? BTZ, you know this mapping, right? Poincare ADS3, right? And then you can, this is a ZT, ZXT, then you have this low coordinate, low and y and maybe t, right? Coordinate. D rho squared. So you can have. So always you can write this. I think anyway, you need this kind of chain. Maybe if we write this, which is symmetric like tau, so you have a coordinate system and you can go this way. Is this okay? And so you can also do KK reduction. Okay, yeah. I think so. But yeah, I think so. Because anyway, BTG is a kind of orbifold of pure ADS, right? You can also get BTG by orbifolding this guy. So you can think this, you can start from this configuration and you can take orbifold and reduce to a lower dimension. Okay. Any other question? Yeah, sure.
In the last picture of holographic derivation of page curve,
yeah,
I didn't see why the black hole is involved in the discussion.
Okay, but the black hole is actually here, actually some in the middle. Black hole, so actually there is a black hole horizon. And yeah, location black hole is also important to which one is favored. Like for example, between this guy and this guy, which one is favored and so on. It's involved in the details of this calculation. And of course, this value is black hole entropy. Right? This comes from contribution from here.
So
or maybe maybe this length. Huh?
Without black hole, this picture is not correct.
Without black hole.
This picture also.
No. Actually, without black hole, I mean, we can also have this kind of behavior. That is true.
So page curve is not particular to black hole, not special to black hole.
Yeah, in that sense, yes. In that it's not peculiar. But if you really literally have some interpretation from black hole, you need, of course, black hole setup. But this kind of transition can happen many times. But I think, yeah, but the point is that it goes to zero, right? It goes to zero to get a page curve. That case, we need a black hole evaporation, right? So anyway, if something remains, then it goes to finite value, right? We don't want this one. I think, yeah, black hole evaporation plays a very important role to get final zero. But if we have some similar, analog of page curve without gravity, but it's probably end up with some constant. So yeah, anyway, presence of black hole is very important. In the final step, this evaporates and there are no black hole contribution. Okay.
Quick question about this.
Yes.
So I guess you mentioned that this boundary entropy can be either positive or negative, but later.
Yeah.
But later, in order to say this is G, following G theorem, it should be positive, no?
No. I'm not saying this. G theorem is true, even negative boundary entropy actually. So anyway, yeah, this formula says boundary entropy can be negative because tension can be negative, and the G theorem part is like this, right? So G theorem is just derivative of boundary entropy, right? This is for example G theorem like this, right? So we are not talking about the value of this guy. This can be negative, but derivative should be negative.
But I guess physically this is a defect central charge. How this can be negative?
Defect central charge?
Yeah.
No. This is not central charge actually.
Oh, I see. Wow.
You mean logarithmic piece or something, right? But no, this is not like this. It's just constant part.
This is not the.
Yeah. For example, the case for this, this boundary. If this boundary is like this, then I mean negative. This case is boundary entropy is negative. This case is positive. So if this anyway along this line, if we go this way, right? This way it's positive, but the opposite side it's negative. Very simple reason, right? this angle is less than 90 degree or larger than 90 degree. So that gives a plus minus. But even this case, we just say that angle should be decreasing like this way. This is not allowed. This is only allowed. This guy is allowed. This is G7 tells us.
I see. Thank you.
Okay. Yeah. Thank you for the question. Any more question?
Can we go back to the triality page?
Sorry, could you say again?
Can we go back to the triality page where you have three dualities?
Three dualities. Okay, three dualities. Let's see. This one, right? Yeah. Sorry. Sorry. it will go different way. Let's see. Yeah. This one, right? Yeah.
Well, I'm not seeing it here.
Huh?
Yeah, right. Okay, yeah. No, I see it. So I don't quite understand the two dualities that relate the first line to the second line.
So two duality. Okay, I didn't mention this one, right? This one or this one. Is that right?
Basically, yeah. The second and third.
Yeah. I didn't explain. Yeah, I forgot to touch it. So there is a boundary, right? This is a very naive duality, but we have boundary. And the boundary looks like CFT D-1, right? Because we have a conformal symmetry. This boundary has the same conformal symmetry.
Okay.
And that is actually dual to ADS-D. And this gravity lives on ADS-D because this is also ADS-D. This is ADS-D.
I see. And on the right side, there is no CFT-D, just in the second one.
So right-hand side?
So the second line on the right side, there's only the gravity D without the CFT-D.
Oh, yeah, okay. But there is actually CFT-D. Yeah, that's right. There is a
there is
CFT-D here.
Why?
Why?
Why is that?
Yeah, that's a good question. But this is a little bit complicated duality, you know. What are the best way? But this is cutoff. You know, we have this is not just regular CFT. This is really cutoff CFT. It's a lot of, you know, yeah, you can regard this CFT is, you know, you cannot separate this CFT with this gravity. It's sort of induced gravity, you know, induced gravity. Newton constant, you know, to define gravity, we need a Newton constant, right? A Newton constant induced from CFT. After integrating out all degree of freedom of CFT, then you find regular gravity action. This is what is happening here. So after that, we just have a gravity. You know, you can think effectively you get just gravity, and that gravity is dual to this CFT D-1.
Right. So I'm trying to say. So there, on the right side, you'll have only the gravity D or the gravity D plus CFT-D. Sorry.
Plus CFT-D. But if you integrate, but this gravity is very strange gravity. Actually, no Newton constant because this is induced gravity. Only what we assume is just only metric is fluctuating, and just fluctuating metric and total action is just given by CFT action. No Einstein-Hilbert action. And if you integrate CFT degree of freedom, then Newton constant or Einstein-Hilbert action is induced from this matter.
Well,
and
I thought that
this is a kind of regular ADS gravity.
I thought that the gravity is precisely the ADS2 of the CFT D-1, is it not?
Yeah. That gravity is dual to this CFT D-1.
Right. So in that sense, right. So I'm still confused why on the right there has also to be the CFT-D. I mean, I thought you just replace the boundary CFT D-1 with the gravity D, and then you are done. Why the CFT-D is there on the right?
But if you don't have CFT-D, then this gravity action is just zero. It's action, no action. Only this theory looks like just h mu nu, like this kind of theory. Nothing, no weight here.
But
it should be. And if we integrate out this degree of freedom of the CFT side, then Newton constant. Now you get this. Like this action. Einstein-Hill reduction. And then this looks like regular, ADS gravity. So much looks like dual to, CFT.
Well, I mean, I guess we are still not talking. So I imagine on the second line, so between the left and right, there is no longer the boundary CFT. By the boundary CFT, I mean the CFT d-1.
Yeah.
So you sort of just from the first to the third entries, you basically dualize the CFT d-1 to turn the CFT d-1 to the gravity d.
Yeah.
I thought that's all you have done, and so you just
sorry. So
naturally,
we map this to this one, right?
Right. Well, I cannot see your pointer, so I do not know. Right. So yes, exactly. So in that lower line, there should not be CFTD on the right, should there? I mean, I still don't quite get your argument why there should be a CFTD on the right.
This one, but this one is really a cutoff to CFT. Don't have so much degree of freedom actually. It's so different from this CFT.
It's different from the left CFTD, right?
Yeah, it's so different from same matter content is same as this guy because of this construction.
The same with it.
Same matter content, but highly regularized. Only has a low energy degree of freedom.
Okay, and the reason for you to say that is
it's very non-local theory in some sense. In other words, it's very non-local theory.
The reason you're saying that is what?
Because we are talking about this kind of, you can imagine gravity dual of this surface. It's really cut off, you have finite cutoff CFT, which is highly non-local.
Okay, now you want to
can
use
imagine
that.
some Poincare ADS also. You can just cut in the middle, like you can cut at the ADS radius scale, right? Z is ADS. Then CFT, there are some CFT degree of freedom, but it's highly non-local. It's very highly regularized. So it's so different from this kind of defined CFT.
Okay, so now you are trying to relate the second and the third. So I was talking about the first and the third, but that's fine. We can go to the second and the third. So there. Let me see.
So sorry, can I go and we can discuss later in end of my lecture.
Sure. Yeah.
So because I want one more issue which I'd like to discuss.
Yes.
Okay.
Sure.
So let me anyway try to finish. This is about this derivation page curve from moving mirror model. This actually gives a very simple model using can be computable in using CFT, and we have also nice holography dual. This is based on our recent work and based on the collaboration with Ibrahim Akar and Yuya Kusuki and Noburo Shiba and Jisha Wei. And so this is a moving. So let me start with the moving mirror. This is actually, but the calculation is very simple. I think I don't have enough time, but I think probably I can tell you the main part. So moving mirror is just some kind of, you can prepare some mirror, right? So this mirror, it's like a Dirichlet boundary condition, Neumann boundary condition in free scalar, but I'm talking about more general boundary. Like this is described by boundary conformal theory. But this is simple boundary is of course mirror is just static mirror. This is not interesting. So, but I'm interested in accelerating moving mirror like this way. So initially sit at x equals 0, but suddenly moving under time evolution. And then what happens? What happens is like a particle production, like this way. Somehow non-trivial vacuum is produced. And we can write this profile of moving mirror is z equals zt, x equals zt. X is this location and a function of time, right? And z is just function. But always we can conform map to simplest setup, right? So that's the reason we can calculate many things by using this moving, using conform map. I'm talking about 2D case, right? 2D. I'm talking about interested 2D so that we can use conform map technique. And yeah, let's introduce U and B, and U is a T minus X, and B is T plus X, right? And so the new coordinate T tilde X tilde, and we have X T tilde minus X tilde, and there are some non-trivial mapping between them, and only U coordinate, left moving. So we only have a non-trivial, mapping between this guy and this guy. And the incoming wave is always vacuum state, so we don't do any conformal transformation. Only conformal transformation for U coordinate. And the P is fixed related to this profile of Z, right? I'm just solving this. And for any profile of Z, you can find some P, function P. And so that we can always describe, moving mirror by using conformal map. And you can calculate energy flux, right? This is just a Schwarz derivative contribution, right? And in this coordinate system, there are trivial, right? This is everything trivial. There are no energy flux. Energy flux is 0. So you can go back to original coordinate and get you can calculate the energy flux, okay? And this is this value. And that we are particularly interested in some example, which is like this profile. Let's take this profile. So this is the reason we find this profile is this is, kind of analogous to like black hole setup. So this is like this. You can this setup. You have this mirror is going this. Initially it's x equals 0, but suddenly accelerating and approaching to x light cone. This is light cone. T x equal minus t, and it approaches. And in this setup, you can compute this energy stress tensor like this form. And at the U goes to infinity, that means later time limit. This energy flux approaches constant value. C over beta is this beta. Actually, beta is inverse temperature of black hole. You can interpret it because this energy flux agree with thermal flux at temperature T equal 1 over beta. Okay. And again, you can conform map, like here, and then what you get just static mirror, right? And but the interesting point here is actually this in this coordinate, this is a full region, but this full region is filled here, right? Only part of the extended space-time. This part is missing, right? This part is a horizon region. And this is analogous to what happening in black hole, right? So we cannot see inside the horizon, outside of observer. So this by using conformal mapping, we get a larger space. So this is a very important aspect. And you can calculate entanglement entropy, right? We can calculate entanglement entropy. So this is a moving mirror setup, but we can conformal map to simple setup with a single boundary, a static boundary. And you can have a subsystem A here, okay? And to calculate entanglement entropy, you can put some single twist operator, right? Twist operator. One twist operator. This is a one-point function, but the one-point function is non-zero in the presence of boundary. Right? In the presence of boundary, this is one-point function. It's non-vanishing. It's just determined by conformal dimension of this operator, delta n, right? And L is this length. And after using this conformal map, we can we have this A. We can conformal map to original system. Right? We take this A to be semi-infinite initially, semi-infinite, so that we can calculate it in universal way. This is the end point is x0, right? And x0 extend to infinity, right? The semi-infinite subsystem. And then we can calculate a conformal map to this length L, right? The x0 is related to L. And we can calculate entanglement entropy this way. Okay. And this is just the x plus this part, just the length L, the same as L. And the epsilon is cutoff scale, but there is extra factor because this combination, right? This is a derivative of conformal map, is precisely cutoff scale in this coordinate. Delta is cutoff scale, but the cutoff scale in original coordinate epsilon is different and differ by this factor. And also, we always have this discomposition, so dispersion function have interpreted as a boundary entropy. Always we have some boundary entropy contribution. And so then now we plug this, now we plug this P function P, then we have linear contribution. We can just put it in log and exponential, so it's like linear. And also we have logarithmic time evolution. But more a little bit complicated. There are two non-trivial dependence, but you can have a better, simple setup if we slightly change the choice of subsystem. So this is a moving mirror. This blue line is a moving mirror. And we choose subsystem A right, to be semi-infinite line. But let's take this location of the endpoint is time dependent, just parallel with this moving mirror, right? Like this linear growth, like this way. Let's take this way because so that distance between mirror is always same. Right? This is a much clear calculation. And in that case, we can calculate entanglement. Only this part is drawn and some coefficient changes, but basically we get a linear behavior, right? Under this kind of change of subsystem, then entanglement entropy linearly growing, right? Linearly growing, like this way. And it looks like temperature. This much like global quench, of in time-dependent background. But the reason why we have linear growth is very clear in this in terms of this particle production or entanglement pair production. Actually, we can work out where this entanglement pair is created in this model. Actually, the answer is like this. PU is a right conformal mapping. B plus PU equals 0. That is really this dotted line, purple dotted line. Along this line, we expect particle production like this way. Entangled pair. It's there. This is a conformal field theory, so the entangled pair propagates at the speed of light in both ways. So here it's created, right? So then one of the pair goes to A, so that means these two guys are entangled, right? This contributes to entanglement entropy. And if we go further, then another one, they contribute. That way we have a linear growth of entanglement entropy. This is very clear. And it has a nice quasi-particle description. But if we want to go further, you need some holographic description. So for single interval universal, right? Single interval, semi-infinite interval is semi-infinite line is universal because it's just 1-point function, and this 1-point function in boundary conformal field theory is universal. But if we talk about 2-point function, a single interval, then no longer finite interval is no longer their universality. So the result depends on, because it's much like 4-point function in CFT. It depends on the theory. So we should choose some particular theory. Let's choose this holographic CFT, holographic theory. That means large central charge and strongly coupled theory. So then we can again use conformal map technique. There are some way to, this is called Barnard's map. We can upgrade the conformal map to bulk coordinate transformation, right? This is precisely, it explicitly like this way. So we have just, in the end, we have just standard Poincare ADS and with some just static mirror, right? This is exactly ADS PCFT. ADS PCFT introduced this surface Q, and this is just boundary. And we just restrict half of the space, right? This is exactly static mirror setup for gravity durable static mirror and do some coordinate mapping. And then we have a moving mirror setup and very non-trivial. For example, if we calculate entanglement entropy, right? Entanglement entropy, then so this is subsystem A is sitting here, right? Subsystem A is here, and then minimal surface we can calculate. In this picture, it's obviously minimal surface is this one, right? Just this one. It's end on the Q, right? As we already mentioned. But in this picture, actually, this surface, this guy actually go beyond the horizon. So that means we cannot, this guy go infinitely, but it never reaches this point, in the point. Because this coordinate system only covers part of the space-time. We should extend, right? Like black hole geometry. So this kind of thing. But anyway, here are explicit plots by taking full contribution. So we can calculate this entanglement entropy for finite interval. So finite interval like this, right? And then we have two different phases, like disconnected phase and disconnected phase. This is the end of the world, right? Surface Q, right? Surface Q here. And yeah, so this dotted line is connected result, and this thick line is disconnected result. The overall result looks like this way, right? This way. So initially growing, but because the subsystem is now finite, so at some point it's saturated, right? Value is saturated and goes to constant. This is a holographic result and explicitly given by this formula. This is disconnected case and this is a connected case. And you can calculate the same thing by using free Dirac filament. This is different theory. And as I told you, so details are different. So this finite interval entanglement entropy is not universal. So you find some different results, but it's qualitatively similar, right? It's linear growth and saturate. But in holographic case, we have this initially disconnected phase favored as suddenly phase transition to connected phase. That's small difference. Anyway, and but now the point is, the final point is we can what about page curve, right? So we want to mimic kind of page curve. Page curve means we have some black hole evaporation, and some system disappears, and we can actually model such a situation like changing the location of mirror twice actually. So we initially accelerate, right? And previously I just talked about this kind of profile, right? And accelerating and toward this velocity of light, right? Just goes to velocity of light. But at some point also again going down and speed down and just goes to static. This is a double kink, right? This kind of double kink profile. And then energy flux also looks like this, and they are negative because of some quantum effect. But roughly speaking, we get the energy flux is coming here, coming here, coming here, and at this point it suddenly stopped. So this is much like Hawking radiation evaporating black hole, and it's modeling that. So non-trivial thing happens only in this interval. And in this case, what happened? Right? What happens is like this. So we have this again, this entangled pair production along this curve, and we can have some pair production. So for this subsystem A, this pair contributes, right? And this pair also contributes this one, but at a later time, point is that. So if we have some particle production, but because of this double kink profile, again, they reflect it back, right? So this is a kind of early radiation, but late radiation also coming back later. So both of them pass through A, right? So then there are no entanglement, right? We are talking about the entanglement between A region and outside, but both of them, right? So if these two guys are entangled, but both of them are in region A, there are no entanglement. So that way, in the end, decreasing, right? Entanglement decreasing. And then you will see precise page curve. It's linear growth at some point, and it's suddenly going down, and it's like both are linear. And if you talk about finite, this is a semi-infinitely long case, right? And if we have two endpoints, then because of there are two endpoints, so there are two peaks, depending on some particle pass through here and pass through here. But anyway, this way, so in this is precisely unitary model, and you can derive, a page curve. And yeah, so finally, it's what's the connection to this black hole, like thing that it's very analogous, right? So very analogous because we are talking about this kind of ADS-BCFT setup, and we are calculating entanglement entropy by using ADS-BCFT. This is very similar to what I mentioned, right? So there we can decompose this area of minimal surface into two parts, this part and the other part. This other part actually, right, boundary entropy contribution. Right, so you remember this calculation of holographic entanglement entropy in ADS-BCFT. So this is the length, but this extra guy, right? This 90-degree, but extra guy precisely agrees with boundary entropy. And this 90-degree part, right here, as this main part. This main part plays a role of bulk entanglement, and this boundary entropy actually is given by this in this ADS-BCFT model in terms of tension, precisely given by this. But this also, you can rewrite this law that probably you remember this formula, right? But by using Brainwashed, holography, I showed you some formula which relates three-dimensional Newton constant to two-dimensional Newton constant, right? By Karuza-Klein reduction, I mentioned. And then this actually precisely 1/4G Newton, two-dimensional 4G Newton. So that means this is really ADS2 entropy. ADS2 black hole-like entropy. If we regard ADS2 a black hole, this is really black hole entropy, right? So that way, so this part, this contribution, it really goes to this area contribution, and this part goes to this in this also setup. And yeah, this is kind of global picture. I don't enough time to explain, but you can think, right? As you can. So this is flat space, right? And this is a brane, Q brane. Right? This part is this part. And this part is this part. And this is the horizon region, which is not covered in the original coordinate system. And this also the horizon region, which is not covered in original this kind of gravity dual. They are connected this way. But anyway, if we define some subsystem S here, and there are some island appears because it's end of some point, and then calculate entanglement involves this, both of them, and we get this form. Okay, so anyway, that way we can have some, this page curve, derivation also, suggest this, interpretation of this island formula. And this is manifestly unitary. And this, you can slightly modify this setup, and you can connect this setup to previous one, which I gave, derivation page curve, just by joining quench. And this is kind of modification of that. You can regard this kind of modification of that. But that once you do the modification, this is just standard moving mirror setup, which should be obviously unitary. Right? So that explained also black hole, unitarity. It's there. I mean, that way indirectly related to each other. Okay, so I think I'll stop here, and maybe it's good to have some questions.
Thank you, Tadashi. Questions, please. But meanwhile, could we all turn on our cameras so that we can see each other, and I take some photos. Meanwhile, please ask questions.
Sorry, could I ask a question about?
Sure. Yeah.
So how the mirror profile is quite special. So it's a unique way, or there are some artificial way?
Yeah, no, actually, you can choose any mirror profile you like. It's arbitrary because this conformal mapping, we have this conformal mapping, right? P. This is just the degree of freedom. You can choose any function of P, and that is precisely the same degree of freedom of Z.
So
but
that
if
means
you choose, sorry, yeah.
So that means the quantitative final result is does not change.
Quantity, yeah, changes. Result of course depend on P, very highly depend on P. Yeah, so if you choose generic P, so there are no, you cannot compare result with any black hole like calculation. It's you just get some different setup. Okay. You can also understand this as this energy flux. It's really depend on P, right?
Right.
That if you choose some particular P and calculate energy, roughly you can understand what you are doing actually, I think.
I see.
Yeah, but anyway, this exponential behavior, when U is very large, like this exponential decay in this choice, this exponential decay is very crucial to get this constant energy flux, much like black hole evaporation, right? Like much like Hawking flux.
Okay. Okay, thanks.
Can I ask you a question?
Sure.
In case of gap theory, one can consider some ADS space which is artificially truncated at some point. And can you view it as a brane setting at a constant Z?
Sorry, you mean gap to phase?
Yeah.
Gap to phase, you mean, I mean, brane is always, gap to phase is described by sort of ADS soliton. Maybe just try to invent. So typically gapped ADS CFT. Typically gap to phase is like ADS space, but with some kind of tip, cap off geometry. So you have Z equals 0, right?
Mm-hmm.
Brane is here. I mean, boundary is brane like this. And this part plays a role of mass gap.
So what is the curve you wrote?
This is a kind of metric, I mean, behavioral metric.
Yeah, and
Yeah, okay, so maybe you can just write the physical region, it's like some Z0, right? And the only physical region is here. And space-time vanishes in this region.
And my question is the constant Z equals Z0 plane, or in the left figure, the blue line, blue curve in the right, are they can they be viewed as a brain?
No, it's not brain, just geometry, just geometry ends. So, I mean, just geometry looks like Shiga, and just this point. This is just smooth point, no brain at all.
Okay, thank you.